Welcome to solverfy.
This is chapter 27, problem number 60. We are given a mass spectrograph, and we want to calculate the mass of an ion in terms of magnetic field, the speed, the radius, and the charge that the ion has. So in part A, all this the ion is accelerated by a potential difference, so that it's going to gain the potential energy Q times V, and this potential energy is going to convert it into the kinetic energy, which is 1/2 mv squared for this ion. Now, if we write the speed in terms of the potential and the charge, then what we have is Q times V equals 1/2 mv squared. The first V being the potential difference, the second one, the one with the tail, is the speed, right? So then if we multiply both sides by 2 divided by m, what we have is v squared equals 2qv over m. Then taking the square root of both sides, the speed equals square root of 2qv potential over m. Now we know that there is going to be the magnetic force acting on this ion QVB. That's going to be equal to, from Newton's second law, mv squared over r. So then these v's are going to cancel. What we have for speed also is bqr over m, right? So then bqr over m has to be equal to the square root of 2qv over m, because the left-hand sides are corresponding to the same thing, which is the speed, 2qv over m. And now I'm concentrated in these two equations. How can we isolate m, the mass, out of this? Because that's what we're looking for. Then let's multiply both sides by m and divide both sides by square root of 2qv, square root of 2qv. Then what we're going to have here is the square root of m, right? Square root of m equals, these are going to cancel, bqr over square root of 2qv. So if you take the square of both sides, then we have m equals b squared, q squared, r squared over 2qv. Let's cancel 1q. So then we're going to have b squared q r squared over 2v, v again being the potential. So we wrote the mass of an ion in terms of the potential difference under which the ion is accelerated, the magnitude of the B field, and the radius of the circular trajectory. Now in part B, we're going to use that expression in order to calculate the potential needed for a singly ionized carbon-12 atom. So again, let's remember m equals q b squared r squared over 2v. Now we want the potential, so we're going to multiply both sides by v and divide both sides by m. These are going to cancel, these are going to cancel. So the potential is going to be equal to q b squared r squared over 2m. Now in this expression, if we plug in values, then q is basically 1.6 times 10 to the power of negative 19 coulombs, right? And the magnetic field is given to us as 0.15 Tesla squared. The radius is given to us as 50 centimeters, so I'm going to convert that to meters and then square it over 2 times the total mass is, since we have 12 atoms, we're going to have to multiply, in order to calculate the total mass, we're going to have to multiply by 12, and the single proton's mass. So then we're going to calculate the potential to be 2.26 times 10 to the power 4 volts for potential needed for a singly ionized carbon-12 atom. And now in part C, let's go to a new page. In part C, we're supposing that the beam consists of a mixture of C12, carbon-12, and carbon-14 ions. And we want to figure out if we can distinguish purely from the distance traveled. Can we calculate the separation of these two isotopes at the detector? So in order to answer this question, we need to find the individual radiuses, right? What will be the radius if I had carbon-12 atoms, and what will be the radius if I had carbon-14 atoms? And in order to get there, again, the expression that we had, m equals q v squared r squared over 2v. Now what we're dealing with is, again, the radius of the trajectory, right? Now let's try and isolate r by multiplying both sides by 2v dividing by qb squared, 2v qb squared. So these are going to cancel. And then for r squared, we're going to have 2mv over qb squared. Now if we take the square root, then we have what r is. Now, again, we have to compare the diameters, right? Because that's the different distance traveled for each isotope. So then what we're looking for actually is 2r. So now for, let's say, carbon-12, right? Let's start with 14, sorry. So D, I'm going to call this D14 equals 2R14. That equals to, using this equation, 2 times 2mv over qb squared. M being here 14 mass of a single proton, right? So then we can rewrite this equation as 2 times 14u times v divided by qb squared. Then this will be 228uv over qb squared. So now if we do the same thing for our carbon-12, D12 would be twice our 12. It will be 2 times 2mv over qb squared. That would be equal to, m being 12 now, 12u now, we would have 2 times 12u times v over qb squared. Then we have 2 square root of 24uv over qb squared. Now, we want to know if we can distinguish carbon-14 atoms from carbon-12. So we're actually looking at the difference between the diameters. So delta D is what we're looking for. Delta D then is going to be D14 minus D12, right? So if we do that, what we're looking for basically is 2 square root of 28uv over qb squared minus 224uv over qb squared. Let's go to the next page. So if that is the case, then 2 times uv over qb squared then is going to be equal to square root of 28u. Sorry, we already carry u here. Excuse me. We don't have to. We already put the u here. We don't have to repeat that. So then minus square root of 24. Right? Then we plug in for u. What we have is 1.66 times 10 to the power negative 27 kilograms. And the potential we had calculated to be 2.26 times 10 to the power 4 volts over qb be 1.6 times 10 to the power negative 19 coulomb charge of a proton, and then the square of the magnetic field. These are all under square root. And then we have square root of 28 minus square root of 24. So then when we calculate everything, we're going to find that separation to be 8 times 10 to the power of negative 2 meters, which corresponds to 8 centimeters, which is quite distinguishable.